Yes, how are you all? Okay, so as we all know, this is a lecture scheduled for KVPY. Good evening, everyone. Okay, so we are going to be taking two very important topics for both 11th and 12th standard in chemistry, and we are going to take the questions related to them too. Okay, so first we'll understand the theory behind it, and then we'll try to solve some problems related to this. Okay. So solid state and thermodynamics, I think, are the most important chapters as far as part one is concerned in chemistry. That means from physical chemistry, right? So both of these chapters, and I was seeing that, in many of the papers, almost every paper contains at least one question based on these two topics. Okay. So when I talk about solid state, I am sure everybody knows and everybody is very comfortable with solid state. Yes. So just let us look at the introduction related to states of matter first. Okay. Yes, we all know the general characteristics of solid state. We know that they have definite masses, volume, shape, all this we all know. Okay. Can anybody tell me what are the four types of solids that we have? Yes. Can anybody tell me the four types of solids that we have? Can anybody name them, please?
Ma'am, I can tell.
Yes, yes, sure.
Ma'am,
Yes.
first one is ice, and second one is duster, wood materials,
Okay, okay.
and
Do we have specific
third
names for them?
and third is glasses,
Okay.
and
All
fourth
right, all
is
right.
human beings.
Okay, okay. Okay, very good. So, see, I'll tell you one thing, okay? Yes, I can also see Aryan, you've told me the three types of solutions that we have. Yes, that is the states of matter, okay? So, gas, solids, liquids, Bose-Einstein condensate, and even plasma. These are the five states of matter, okay? What I am asking are the four states or four types of solids, okay? We are going to be studying solid state in detail. We are going to be looking at the different types of solids that we have, okay? So, before we go to that, I just want like to introduce you all to a term isomorphism and polymorphism. Okay, what is polymorphism? If I had to tell you in simple terms, okay, I'll give you an example for polymorphism. What is polymorphism? Suppose identical twins, okay, or non-identical twins, okay. For example, they have the same genes, they are coming from the same parents, everything is same in them, but still their appearances are different. Yes. So these types of uh, substances also, even in solids, when we see that they are made up of the same substance, like suppose they are allotropes of carbon, you must have heard. Yes, everybody knows allotropes of carbon. All the three allotropes that we talk about, all of them are made up of carbon only, but still you will see they, when you look at them, you will not be able to recognize them, and they will be completely different. Yes, very good, Ansh. We have diamond, fullerene, and graphite. All three these allotropes, all of them are made up of only carbon, but still when you look at them, do you recognize that they are made up of carbon only? No, their appearances are completely different from one another. Okay, and that phenomenon is said to be polymorphism. Okay, so when a single substance that exists in two or more forms or crystalline structures, it is said to be polymorphous. And what is isomorphous? When two or more substances having the same crystal structure are said to be isomorphous. Okay, different substances having same structure, isomorphism. One substance having different structures, you call it polymorphism. Okay. Yes, same crystal iso, different crystals are allotropes. Very good. Okay. Now we are going to go to the classification of crystalline solids. Okay, this was the four types of crystalline solids that I was asking you all. Whenever we look at solids, okay, all of them have the same properties. The force of attraction between them is very high. All that is very similar. But still, there are some differences among them, okay? And we have four different types of solids: ionic solids, covalent network solids, molecular crystals, and we have uh, metallic crystals or metallic solids. Okay, so can you give me an example of ionic crystals? Anybody? Any solid that you think? Okay, only Na. Ionic crystal. Any crystal or any solid that you think? Okay, Na plus. Okay, tell me the entire crystal, my dear. Ansh, just tell me a crystal that you know of or any solid that you know of which is made up of two different ions. Okay, what you've told me, I'll just expand that and I'll write NaCl. Yes, very good. NaCO3 also, correct. NaHCO3 we can have. Very good. NaCl. So NaCl is made up of Na plus and Cl minus. Therefore, from the name only you get that it is ionic solid. That means it contains two different types of ions. Okay. So like this, we'll just see the types of all of them. So these are ionic solids. Okay. All salts are crystalline and called ionic solids. Now this you must have studied in 8th, 9th, 10th standard. You must have studied acids, bases and salts. Whenever we classify substances as salts, what we mean by, we say that they don't have H plus ions, they don't have OH minus ions, they have different ions, and therefore we call them generally ionic solids, okay, because they are made up of different ions. The constituent particles of ionic crystals are charged ions. The cations and anions may differ in size. Cations are which charge? Which charge is present on the cations?
Positive.
Very good. Positive and the negative charges, the substances may be different, okay? Each ion of a given size and charge is bonded to ions of opposite Coulomb force, okay? Opposite charge by around 1 Coulomb force. In short, ionic crystals are formed by forces of attraction between ions of opposite charges. So everybody knows this. That is how we get the formation of NaCl, right? Na gives the ion, or Na gives the electron, Cl takes the electron, and there is a force of attraction between them because they are oppositely charged. Ionic crystals are hard and brittle. What do you mean by brittle? Brittle is what? Yes? Hard and brittle is what? Brittle means something that you can break down very easily, okay? Just if you take it in your hand and you press ionic solids, you can break them down, okay? So that means brittle. Yes, which breaks easily. Very good, Ansh. They are non-conductors of electricity in solid state. However, they are good conductors when melted or dissolved in water. So suppose you take an ionic solid and you put it into water, you will easily get a conduction of electricity. Now I have one question based on this. Tell me please, which of the following is not an ionic in solid state? This is a question from your book only. So which of the following is not an ionic in solid state? For that, a hint that I could give you is recognize the ions that are present in all of them.
Second.
Second is what? B, PCl5.
Yes.
Why?
PCl5 makes a covalent bond.
Okay. Actually, see, the basic recognition is to identify the ions among them. Okay. See, whenever I will take this is made up of N2. I'll tell you the ions that are present in all of them. Okay. We have NO2 plus and NO3 minus ions. Okay. So this is definitely an ionic solid because it is made up of these two ions. Okay. Sorry, NO3 minus. Okay. Now when I talk about PCl5, okay, we'll come to PCl5 later. First, let us talk about this. It is made up of XeF5 plus and F minus ions. Okay. Now, sorry. You all tell me what are the ions present in ICl3 and what are the ions present in PCl5? Do we have ions in ICl3? What are the ions that you can recognize? Yes? Anybody? The correct answer to this is but only you should remember that only ICl3 is a compound which exists as a dimer. So the correct answer is C, ICl3, because only ICl3 is the compound which exists as a dimer. Yes, I2 and chlorine which cannot form ionic bond. Yes, and they always exist. If I had to give you the structure, it is something like this, okay? The dimer exists like this. It has a square planar structure. So every iodine is bonded to like 4 chlorine atoms, and you get I2Cl6. Sorry. No, it is not tetrahedral. It is square planar. It is almost planar structure. Okay? So you get a square planar shape. And the hybridization over here, yes, the hybridization, if you want, I'll just tell you, it is sp3 dehybridization of iodine. D also. If it would have been sp3, then Ansh, we would have got a tetrahedral geometry. Yes? But because we have sp3d, that is why we can say that it has a square planar structure. Okay? Chalo. Got it, everyone? Okay, so these type of questions you need to understand. Just look at the ions that are formed, okay? If you can recognize the ions, you can definitely recognize which one of them is not an ionic compound, okay? Next. What again we have is covalent network crystals, which are the second type of crystals, okay? Here, please remember, the constituent particles are atoms. In ionic crystals, what were the constituent particles? Yes? Ions, very good. From the name only, right? From here, you need to remember they are atoms, okay? Atoms are linked by continuous system of covalent bonds. Again, covalent network, that means they are made up of covalent bonds, leading to a three-dimensional network forming a giant molecule. The entire crystal is a single molecule, and therefore it is also called a giant solid at times. Please remember, you will, whenever you will look at a crystal, whenever you will look at a covalent network crystal, you will be not you will not be able to recognize the individual atoms present in it. Now look at diamond. Diamond is a very good example you need to remember for covalent network crystals. When you look at a diamond, do you recognize all the carbon atoms present in it? No, it obviously appears like a single giant solid. Yes. Right, allotropes, correct. As a result of rigid and strong covalent bonding, covalent crystals are very hard. In fact, they are the hardest and most compressible of all materials. The best technique to remember the properties of any solid, I would tell you, is to remember an example of it. Okay? If you remember the example of that particular solid, you can easily write all the properties. Like for diamond, everybody knows diamond is the hardest substance on earth. So you can easily remember that, yes, they are very hard substances. Yes? Okay. They possess high melting points and boiling points, almost 4,000 we have for diamond. Due to localized electrons, they are not mobile. Okay, that means each carbon has its own position. They are very synchronized, or you can say, each one of them has its own position. And therefore, you will see they do not move from one position to another. For conduction of electricity, what is important? Yes. When will you see conduction of electricity or heat? Only when there is very good free electrons, correct? Free electrons and space are the most important things, okay? Whenever you see that there is localization, that means when an electron can move from one place to another, only then it will conduct electricity. If not, then there will be no conduction of electricity. And here, because there is no space for the electrons to move, there is no localization, therefore they are poor conductors of electricity. Example, an allotrope of carbon, we know diamond. Then another example is quartz, which is SiO2, and we have boron nitride, which is again an example of. Okay. Now, diamond is a very important covalent network crystal. Okay, everybody knows this. Okay, every carbon is bonded to another carbon. What is the shape that we get in diamond? Every carbon is bonded to other carbon by which shape?
Tetrahedral.
Very good, tetrahedral. Okay, so like this, you get a huge chain of structures, and where you will see every carbon is bonded to another carbon by 4 carbons. Okay, that means tetrahedral structure. Strong covalent bonds between sp3 hybridized carbon atoms make diamond the hardest solid with a very high melting point of 3550 degrees Celsius. It has been reached up to 4000 also. Next, we are going to study the third type, which is molecular solids. Please remember, again here, from the name only, you can recognize that they are made up of molecules, okay? Like you have Cl2, chlorine molecule, hydrogen molecule, methane, carbon dioxide, all these molecules, okay? When they are in solid state, please remember. The bond within molecules are covalent, held together by strong intermolecular forces of attraction. So depending upon the nature of intermolecular forces, in molecular solids, you have 3 types, okay? So depending upon weak dipole-dipole interaction, very weak London forces, and you have intermolecular hydrogen bonds, okay? So just remember the examples and, okay. So you can see whenever there is weak dipole-dipole interaction, dipole-dipole interaction means what? That means the interaction which is arising due to presence of charges. Okay, so we have HCl, H plus Cl minus, right? H2O, again H plus OH minus. So here there is a very weak dipole-dipole interaction. Then you have London forces, okay, and you have compounds showing hydrogen bonding. What is hydrogen bonding? Yes, do all molecules show hydrogen bonding? Yes, what is hydrogen bonding? In which molecules will you see hydrogen bonding? Hydrogen bonding is the bond between hydrogen and hydrogen. Are you sure, Ansh?
Between a negative oxygen and hydrogen.
Okay, very good. Just remember, it's not just oxygen. It can be hydrogen bonded to any other. I'll write X over here, okay? By X, okay, I'll write, okay, X means any electronegative atom. Yes, electronegative. Any electronegative atom. And which are the most 3 electronegative atoms, do you know? Fond, very good. Please remember the sentence. Fond is fond of electrons. Okay, I'll write it over here. Fond is fond of electrons. That means the most electronegative atoms are fluorine, oxygen, and nitrogen. So Fon is fond of electrons. Okay, so we have fluorine, which is the most electronegative. Then we have oxygen and we have nitrogen. So hydrogen can be bonded to any of these. Okay, it can be bonded to fluorine, oxygen, nitrogen. And that bonding will said to be hydrogen bonding. Okay, and the last type that we have is metallic. In metallic crystals, what we have is the constituent particles are atoms of same metallic element held together by metallic bond. Metals are malleable, ductile, and they are good conductors of electricity. Okay, so all the metals, all the solid metals that you see, all of them will be classified under metallic solids. Okay, now we move on to something known as a unit cell. So everybody knows what is a unit cell. Look, a solid is a very big structure. Okay, we just now said, yes, we just now said that, they are huge, giant solids. But when we want to study the properties and we want to study the number of atoms in them, we have to break down or we have to come down to a very small unit, which is the unit cell. Okay, like in our human body, we have so many cells. So when we talk about the entire human body, it is important to first understand what is present in one cell. If you understand that, then you can correlate with all the others. Similarly, if you're talking about solids, you have to first understand what is present in one unit cell. The smallest part considered for studying in cubic solid crystal is known as unit cell. Very good. Also, you can say it is the smallest repeating structural unit of a crystalline solid. Okay, something which you'll see again and again. Many unit cells, one bonded to the other, second bonded to the third. Like this, you'll get so many unit cells. combining and giving you the entire crystalline solid. When unit cells of same crystalline substances are repeated in space in all directions, a crystalline solid is formed. Okay, so I hope everybody is comfortable with these terms, and please remember, based on the classification of unit cells, we are going to have 3, or you can say 4 types of unit cells. Everybody knows the first one is simple cubic unit cell. Then you have BCC, that is body centered cell, and you have FCC. N centered is generally not considered, and we don't talk about N centered that much. These 3 are the most important unit cells that we are going to be talking about. And you will see in your questions also, there are many questions dependent upon this. Okay. So before we proceed, I'll just tell you, yes, SC, very good. BCC, FCC, and ECC. Okay. So in cubic lattice, there are 14 Bravais lattices. Okay. Out of that, we are only going to study cubic unit cell. Okay. Cubic unit cell is the one that you see over here. See this one. This is one unit cell that I've shown. Like this, we are going to see for simple cubic cell, body-centered cubic, and face-centered cubic. Okay. So simple cubic means that where can you see the atoms? Just zoom in and just tell me where can you see the atoms in this unit cell? In simple cubic. Where are the atoms present? On the vertices. Very good. Or only you can say at the corners. Yes, at the vertex or only at the corners of the uh, unit cell. What about body centered? Please remember, in all 3 you will have like atoms at the corners also. Along with that, in body centered you will have one atom in the center also, in the center of the body of the unit cell. And face centered you will have at the 8 corners. Very good. And along with that, every face will have one atom also. Okay. So we'll directly go to what is very important, is the number of atoms in there. Okay. Please remember, a simple cubic unit cell, you can see that 8 atoms are present at all of them. But in reality, if you see how many are present in one unit cell, see, if you divide this circle, and this is the cubic cell, okay? So it is getting only 1/4 of this, or you can say 1/8 of this. Yes? Yes or no? The unit cell is getting only 1/8
Yes.
of the cubic of the atom, and therefore like this, from the 8 corners of the cube we get 1/8 into 8, which is only 1 particle is present per unit cell in an simple cubic unit cell. It is not 8 atoms. Please remember this point. These are not 8 different atoms, although they are present, but they are shared by 8 different unit cells. And therefore, in all, we will see that only 1 particle is present per unit cell. What about BCC? In BCC, how many particles are there? 2. Very good, Ansh. Can you explain how to? So 1 particle from the corners and 1 from the... This is how you get in BCC. Very good. 1 at the center. This one, the red one that you see, is that shared by any other unit cell? No, that belongs to this unit cell only, and therefore that is considered as one entire, and this is considered as one. So therefore you get like this, 2 particles in BCC. And what about FCC? You have 4 particles per unit cell. Please remember this point, okay? All right. Now we'll come to solving a question. In FCC lattice, A, B, C, D atoms are arranged at corners. So A is present at corners, you can see. B is present at the face centers. C is present as at octahedral voids. And D is present as the tetrahedral voids. So is there anybody who does not know octahedral and tetrahedral voids? Is everybody comfortable with these terms?
Voids means?
voids means the spaces that are present in between them. Okay, 1 second. We'll just go to the next slide. We'll come back to this question, okay? I'll just explain this thing first. Yes, empty spaces, okay? All right. Okay, see, you can see over here. I'll directly go to FCC packing. You'll understand. Okay, look over here. Can you see the space? Although they are arranged very close to each other, can you see the space over here? Yes, yes, that is known as a void. Okay, that is a space which is always present in a crystal. Okay, no matter how closely. Now you cannot overcome this void. Yes, you have to have, whenever you will see solid, there will be this void. You will never be able to overcome it because there is no possibility you can arrange them in such a way that you can overcome this void. Now, depending upon how it is formed, you have different voids. Very good. Octahedral void comes from octahedral shape. Okay. See, I'll explain over here. This is first of all known as, okay, we'll go to directly octahedral and tetrahedral. Okay, this is octahedral void and tetrahedral void. When three spheres are present, the blue spheres, okay? Void is filled by impurities as it does not belong to the lattice itself. Yes, very good, Ansh, correct. So see, you have these spheres 1, 2, and 3. Okay, all these three are present on the first layer, and above them you have placed another ball. Okay, but there is still this void is there. So because it is formed by the shape of a tetrahedral, or you will see which is formed by a tetrahedral shape, therefore it is called a tetrahedral void. Whereas the one which is formed by an octahedral is said to be octahedral void. Okay, please remember this point. Okay, so we'll go back to this point where we. Yes. So now you tell me, if you arrange the atoms like this, if you have an FCC crystal lattice, okay, that means where are the atoms present in FCC? In FCC, where do we have the atoms? Corners and face centers. Very good. So if you have a cube like this, so what you can see is you have to tell me how many atoms are present at the diagonal. Now look at the diagonal, okay? The diagonal will be difficult to show you, but I hope you understand. This is the diagonal. Yes? Can you understand the diagonal?
Yes, ma'am.
Okay, very good. So now you tell me how many atoms. Okay. Do we have anything? Is there any face coming in between? Yes? No. So that means that no atom will be present at the face centers. That means B will definitely not be there. Why B will not be there? Because there are faces. What do you mean by faces? The faces are, the surfaces at the, what you can say, the faces of the crystal or the cubic cell. See, this is the first phase. Then the above phase, the surfaces you can say. Okay? But when you look at the diagonal, you don't have any face in between and therefore you don't have any atom present over there. That means no atom is present at that the B atom, which is the atom present at face centers, will not be there. So here only you have classified or you have eased your method and you've got your answer will be somewhere between A and B. Okay, now you only tell me, will it be A or will it be B? What do you all think? How many atoms will be present in octahedral voids and how many will be present at tetrahedral voids? A option. Okay. All right. For that, I would just like to give you a hint. And this is the hint that you need to remember. That whenever you will have in FCC crystal, please remember, the octahedral void has to be there. I told you the octahedral void will be there. Yes? And here they have not given any octahedral void in option A. They have completely omitted octahedral void. They are saying that only tetrahedral void is present. So therefore, the correct answer is B. And please remember, number of atoms. See, if you look at this diagonal, you have this atom coming across and this atom. So two A atoms, one of the octahedral atoms and one of the tetrahedral atoms. Got it? Very good. Okay. I would like everybody to just take a screenshot of this because these are the important parameters of a unit cell. Okay. Many a times edge length formulas are given and you have to calculate the edge lengths many a time. So we'll come to the edge lengths directly and we'll understand all of them. Okay. All right. So packing is done. You have different types of packing. You have HCP, you have FCC and all of that. Now this part is VVIP, okay, where radius of a sphere, so many times they have asked, so many times radius of a sphere has been asked, okay. They will ask you, how will you calculate the radius of the sphere, or they will ask you the edge length. What is edge length? See, this A is the edge length, okay. This is given by A, okay. That means the length of one edge of the, yes, this is only for simple cubic, please remember. For others, we will come to that also very soon, but this is for simple cubic, okay? So in a simple cubic lattice, you will see that the edge length A, what is edge length? Edge length is the length of one of the edges of the unit cell, okay? Now, because it is a cube, all of them will be same. So therefore, it is given by the letter A, which is equals to 2R, okay? So please remember, for SC, A is given by 2R. Okay. Next. Okay. The edge lengths of the unit cells in terms of radiuses of spheres constituting FCC, BCC, and SC are respectively dash. You have to tell the values of A. And to know the values of A, you should know the formula of the ones that we were just talking about. For FCC, for BCC, and for all of them. Okay, so I'll just make a column over here. Yes, everybody please write this down. Many times questions have been asked on this. Okay, first we'll write the formula for A, and from that we'll write the formula for R first, that is the radius first, and then we'll calculate for A. Okay. So according to you, option is between B and D, this is for sure. Okay. Alright, very good. We'll just come to that. First, you tell me, what is the formula for R? Just now we saw what is the formula for R. Yes, anyone? A by 2. Very good. That means A was equals to 2R. What about BCC? Does anybody know for BCC? Okay, first we'll write for FCC because that is very simple. It is 4R by root 2. Okay, and when you come to R, you get, okay, A is equals to 4R and you get, everybody please write this formula. What else? I think I've written it. 1 second. The correct answer for that is the D1. I've already written it. Who said it was between B and D? Yes, Ansh. So the correct answer is D. How it is D? C. Because they've asked you for FCC first. Okay. Please remember, it is FCC first, then BCC, and then SC, respectively. Okay. So like that, you get 2 by root 2R, 4R by root 3, and 2R. Okay. I've also given the values over here for A for all of them. So from this, we calculate the edge length. Okay. That means we have to calculate for A everywhere. Okay. Everybody understood this? Yes. Any questions? All right. Now this one is simple, okay? Copper crystallizes in a structure of FCC unit cell. The atomic radius of copper is 1.28 angstrom. What is axial length on an edge of copper? They have only twisted the words. They are asking nothing else but the edge length, which is A. So you have to calculate A for an FCC and they've given the value of R. Yes, so can you all calculate please? What is the formula? Just now we wrote the formula. What is the formula for FCC? Very good, 4R by root 3. Okay, are you sure it was root 3 for FCC? Root 2. Very good. So you get the formula A is equals to 4R by root 2. Okay. So you have to calculate R is already given. So 4. Let us keep angstrom as it is. Let us not convert it. Okay. Divided by root 2. So what is the answer? Yes, please calculate the answer and tell me. Is it A, B, C or D? If you calculate 4 into 1.28, keep the angstrom as it is. Okay, don't convert it into meters because you have the answer in angstrom also. So divide by root 2. What is the answer? How much is root 2? B. Very good, Kunal. Very good. So the correct answer is B is given by is 3.62 angstrom. Everybody please try this and check whether the correct answer is this only. Okay, the correct answer should be 3.62. Okay, very good. Also, this is a very important thing you need to remember, the packing efficiency. Okay, packing efficiency in simple cubic unit cell, you have to calculate, but after calculations, you will see that no matter how closely we arrange the atoms, you will always get a void space. So the void space is very high. You can see in SCC or in SC. The space occupied by particles is only 52.4%, whereas by voids, it is almost 47.64%. Okay. When I go to BCC, now what has happened? Packing efficiency has increased or decreased? Yes. From SC to BCC, my packing efficiency has increased or it has decreased? The void space was more in simple cubic, right? The void space was very high over here. When I came to BCC, the void space has reduced. So my packing efficiency must have increased or must have decreased? Packing efficiency simply means how well you pack the atoms close to one another. If we pack the atoms very close to one another, that means the packing efficiency will be high. In that case, obviously, because we are packing them very close to one another, the void space will decrease. And therefore, you will see when we came from SCC to BCC, the void space has decreased. That means the packing efficiency has increased. Okay. Then I hope everybody is comfortable with crystal defects. I'll just give you a flowchart for that. Please, everybody note this. Okay. So point defects are of three types. In that you have the first one, which is stoichiometric point defect. In that you have vacancy defect, self-interstitial defect, Schottky and Frenkel defect. Then you have impurity defects, okay, wherein you know what happens, an impurity comes and attacks the void spaces, okay, or sits in the void spaces. That is substitutional impurity defect, or you can have interstitial impurity defect. And the third one is non-stoichiometric defect. In that you have metal deficiency and metal excess defect. So everybody please take a screenshot of this and just remember these are the all types of defects you can see in solids. Okay? Got it? Everybody is comfortable with solid state now? Any questions on solid state? Okay, very good. Next, we are going to move on to chemical thermodynamics. Okay, like I said, thermodynamics is again a very important part of your syllabus in chemistry, and therefore it is important to understand. We'll directly go to the very important equations that we have. I'm sure everybody knows what is thermodynamics. Thermodynamics in chemistry is concerned with the energy changes in physical and chemical transformations. Okay, how the energy changes. Okay, that means whether it decreases, whether it increases. Yes, Devdatta, you have any question? You were raising your hand. So what we are concerned is whether the energy has increased or the overall energy has decreased in a chemical reaction. That will tell you thermodynamics. Thermodynamics is going to tell you all about the changes. Okay. However, thermodynamics provides no information regarding rate of reactions or the mechanisms involved. Okay. So it will only tell you that the energy has increased. Okay. Yes, that's in physics. Right, Ansh. In physics, yes, you will understand how it happens, and how what are the mechanisms and all that. But for as far as chemical thermodynamics is concerned, you will only understand what are the energy changes, right? It will only tell you whether the energy has increased, whether it has decreased, or like that. Terms used in thermodynamics. Everybody knows the terms. What is system? What is surrounding? Yes. Do you all know what are systems? What are surroundings? The part of the universe that is under thermodynamical study
Yes,
is said
ma'am.
to be our system. Okay, it will change from reaction to reaction. That means when I'm talking about a reaction in the laboratory, my system is different. When I'm talking about, yes, system on which the experiment is conducted, and surrounding is everything around the system. Very good. So what is system? A part of the universe under thermodynamic investigation. Okay, all other parts outside the universe are uh, surrounding. Outside the system in the universe are surroundings. Okay, so if you can see in this example, I've taken a gas and I want to check whether the gas is expanded or it is compressed and all of that. So my gas is under study under thermodynamic investigation, and therefore it is the system. Whereas everything, the cylinder, the room in which the experiment is conducting, everything else becomes the uh, surrounding. Okay, so what are the three types of systems that we have? From the picture itself you all can recognize. Yes, please remember this point is very important. Yes, open systems, closed systems, and insulated. Very good. So in open system, both heat can transfer, mass can transfer. In closed system, only heat can transfer, mass cannot transfer. And in isolated system, heat can also transfer. No heat transfer, no mass transfer. Okay? So that is all you need to remember about the three types of systems. Okay? So there is no exchange of mass, neither matter. Now we are going to see intensive properties and extensive properties. Okay, I hope everybody knows these terms. Yes, I am comfortable. Okay, the properties which depend on the matter present, they are known as extensive, and the ones which do not depend are said to be intensive, or you can say which are independent. Okay, like temperature. If suppose I take 1 ml of water and if I take 10 ml of water, both of them will have the same melting point, same boiling point, sorry. Yes. What is the boiling point? Both of them will start boiling at 100 degrees Celsius. So no matter how much amount you take, the temperature or the melting point is going to remain, the boiling point is going to remain the same. And therefore, it is considered as an intensive property. Okay. What are state functions? Can anybody tell me what are state? Very good. Intensive are independent of substance. Okay, very good, Ansh. And the extensive properties are dependent on the substance. What are state functions? From the name itself, you need to remember state functions and path functions. So how will you define state functions? Anyone? Yes? Please remember state functions are the functions which will only tell you the properties which will only define the state of a system. The property which depends on the state of a system and independent of the path followed to attain it is called a state function. Like for example, yes, depends on the change of state. Okay. If suppose the temperature was first 0 degrees Celsius, or let us say it was 10 first, and now it has become 100. Okay. So what do we know? We know that the initial temperature was 10 and the final is 100. Do you know how it has changed from 10 to 100? Yes? Is it necessary to specify how it is changed from 10 to 100? Yes or no? No. And therefore, you will say it is a state function because it does not depend upon how the path has been followed to attain that particular temperature. Okay? It only depends on the initial and the final states. It does not depend upon the path followed to attain it. The best example or the best technique to remember is remembering the examples of path function. There are only two path functions. Apart from that, everything else will be considered under a state function. Yes, Raj, any problem? Okay. So what is path function? The property which depends on the path is called the path function, okay, which depends upon how you have changed the temperature, whether it first increased, whether it first decreased, everything when it is specified, it is said to be a path function. There are only two properties which are path functions, that is work and heat. Rest everything is a state function. Okay, got it? Okay. So please everybody take a screenshot of this and remember this. This is very, very important. Okay. The various processes in chemical thermodynamics, there are 5 processes involved. Number 1 is an isothermal, isobaric, isochoric, adiabatic, and reversible processes. All are very, very, very important. You have to remember the properties, or at least the ones that you see in blue, that is very important. Okay. For isothermal, I've written delta T is 0. That means the temperature, delta means change. Okay. So there is going to be no change in temperature. That means temperature is going to remain constant. In isobaric, the pressure is going to remain constant. There is no change in pressure. In isochoric, volume is going to
Ma'am,
remain
what are
constant.
these processes
Yes.
of process of KVPY, Professor?
Yes, yes.
मैम कैन यू मतलब किसका है ये सब प्रोसेसेस?
These processes actually, these are the processes that you will see in chemical thermodynamics. मतलब क्या होगा? See, when you will see a gas is expanded isothermally. मतलब कि क्या हुआ? Expansion हुआ gas का, but कैसे हुआ? Isothermally हुआ. So that means the temperature has remained constant. Understood? So how a chemical change is going to take place? It can take place by these processes. It can either be isothermal, it can either be isobaric. They'll tell you like this. A gas expands reversibly, or you can say isothermally and at temperature constant. All these different processes will be mentioned. Okay, got it? Yes, Srivardhan, got it?
Yes ma'am, got it.
Okay, all right. Okay. Now we are going to go to nature of work. Okay, now this is VVIP. Actually, please remember this equation. This equation and this equation will help you a lot, okay? Because numericals will be basically asked on this, Delta U is change in internal energy. If you want to calculate the change in internal energy, you have to calculate heat and the work done. Okay. So, okay. An ideal gas expands against a constant external pressure of 2 atmosphere from 20 liters to 40 liters and absorbs 10 kilojoules of energy from the surrounding. What is the change in internal energy of the system? Just now we saw the formula for change in internal energy. What was the formula for delta U? Yes? What was the formula for delta U? Just now I gave you the formula. Q plus W. Very good, Shreyash. Okay. So we have delta U is equals to Q plus W. Okay. What is Q? Q is the heat. How much is heat is absorbed? It is 10 kilojoule. Okay. It is given in kilojoule. Therefore, first you'll have to convert it into joules. Okay. So 10 into 1000. Now, you also, I'm sure everybody knows that the work done is given by the formula. What is the formula for work done? Everybody knows PV type of work. That means the work involved, which is showing the change in pressure and volume. Everybody knows PV type of work. So basically that is the work done over here. And how, yes, force into displacement. Okay, we could use that formula, but because we don't know the force and the displacement given over here, we are going to consider PV type of work. That means the work which is done when pressure is 2 atmosphere and volume is changing from 20 liters to 40 liters. Okay, so therefore you get, and also I'll tell you one thing. Okay, now work is done by the system, therefore work will be negative, so you will have to take minus. Why? Because an ideal gas is expanding. That means the work is done by the system. I'll give you a simple example. Suppose my gas is like this. I have a piston over here. Okay, and this is the external pressure, P external. And this is my system. Okay, my gas is over here and this is my system. Now, when it is expanding, so who is doing the work? The system is doing the work or the surrounding is doing the work when it is expanding? Yes, it has to push this piston upwards. Yes or no? So who is doing the work? Yes? When the gas has to expand, it has to push the piston upwards. Only then it will be able to expand. Yes or no? Very good. By the system, that means on itself. Okay. On the system, by us. Okay, okay. Very good. Right. So by the system, that means the work is done. Over here, if you look at it, the gas has to expand. Okay, so it is doing by itself. It is doing khud se, right? And that is why you will see the work done will be always negative. Okay, so I'll just write the formula here. Please calculate and tell me. 2. What is 2? 2 is the pressure, P. Okay, into volume. How much is the volume? How much is the change in volume rather? W is equals to P delta V. I hope everybody knows this formula. Delta V is how much? How much is the change in volume? It has changed from 20 liters to 40 liters. That means how much is the change in volume?
20.
Very good. 20. And also this is atmosphere. We have to convert it into atmosphere liter. Therefore, we'll multiply by 1.3. What is the answer that we get? Please calculate, everyone. What is the answer? Yes. Did you get the answer? 10 into 1000 minus 2 into 20 into 101.3. B. Very good. Correct, Shreyas. The correct answer is 5948 joules. Okay? And that is why, because it was given in joules, we had to make sure that we convert the kilojoules into joules. Okay? And for that, we multiplied by 1000. Okay? Now, this is very, 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 very important. Okay? Heat is absorbed by the system from the surrounding. Heat is released by the system. Work is done by the system. And work is done on the system. Depending upon that, just now if you see, I took negative for work. Why did I take negative? Because work is done on the system. Okay? So you have to remember whether at what time you have to take which sign convention. Now, in a process, the pressure of a gas is inversely proportional to the square of the volume. Pressure of a gas is inversely proportional to the square of the volume. Is this correct?
Yes, ma'am.
Okay. If temperature of the gas increases, then work done by the gas is dash. Okay. If we want to remove this proportionality sign, what will we have to add?
Constant.
Constant. So let us add a constant K. So what do I get? I get that PV square is equals to K. I can write PV square as PV into V. Yes or no?
Yes, ma'am.
Okay. What is PV equal to for an ideal gas?
RT.
Only RT or N also? Very good. nRT. So what do I get? I'm continuing over here. Okay, I get nRT V is equals to K. Now N is constant, R is constant. So let's not consider that. I get TV is equals to K constant. Now you tell me, if temperature increases, volume will
Decreases.
decrease. Very good. Volume will decrease. If volume decreases, then work done by the gas is what?
Negative.
Very good. Excellent. Did you all understand?
Yes,
Like
ma'am.
this, you need to understand. Okay, so please write that. If you want, you can write that equation, and you will understand. If temperature increases, volume decreases, and if volume decreases, then work done will be negative. Okay. I think I have one more question depending upon this. We'll just complete that question. Okay, remember this equation. Okay. Yes, this equation is very important. W max is equals to minus 2.303 nRT log P1 upon P2. I just have a question depending upon that. You all just try to solve that. If anybody has any doubt, please ask me. Okay. Just take a screenshot of this. You all can solve it, and you can send the answer whenever you all feel. And if you have any doubts, please ask me. Please let me know. Okay.
Okay, ma'am.
Yes. With this, I think we'll stop over here. So thank you very much, everyone, and take care. Bye, everyone.
Okay, ma'am. Bye, ma'am.
Bye.